Hello, I'm Vsevolods from Blockvis. In this video, I'd like to present you a new protocol for storing encrypted data on IPFS. This is work done within the project of creating a decentralized secure store for identity data, which is conducted by Identity.com and Blockvis. This work might be familiar for you because it was presented formally as Duck Onion COSE. But this is a second iteration of the previous protocol, and I think it's fair to say that the Duck Onion COSE was more of a logic model, and what I'm gonna show you today is more of a physical representation of all the data and information. Okay, first of all, a few words about what is changed from the previous implementation or a previous model. We had a lot of discussion about how to optimize the Duck Onion COSE, and there are a few pain points were addressed in this new model, and we think that it became more flexible because we managed to separate the content from the linking metadata, which improved the traversability. It becomes more lightweight and allows to traverse the data graph without the need to fetch the actual content. And we also managed to make it content encoding agnostic. So in a previous implementation, it was heavily relying on DAC CBOR, and this model allows actually to use various content encoding types like DAC CBOR, DAC JSON, protobufs, etc. Okay, before I jump to the protocol itself, I would like to talk about a few assumptions I made for this presentation. And first of all, as I mentioned previously, the protocol is content type agnostic. But for this presentation, we assume that the content is encoded with DAC CBOR. And another important thing is the COSE specification. As we know, COSE supports various types of messages and cryptographic transformations. For example, encryption, signing, authenticated data, etc. And for this presentation, we will touch only the encryption part of the COSE specification. Let's talk about the content which we want to store securely on IPFS. Imagine we have a bunch of files of different types which interlinked between each other in some way. So for the purpose of this presentation, we came up with this graph where each node represents a file. So each letter is a file, and the vertices links between those files. So we can imagine we have file S and file X, which are leaves, so they don't have any linked files, and we have file P, for example, which contains links to file S and X. And we also have two private keys which will be used to encrypt the content. I would like to abstract the users away, because it might be those private keys might belong to different user, or it's just the same user with the different devices, for example. So it doesn't matter for the purpose of this presentation. Having these two private keys used for encrypting the content, we can see that The private key allows to access files and meta information, and we see that, for example, private key alpha has access to file A and hence to file Q and Y. So basically, having access to this private key and the Merkle root of this graph basically means that the owner of this key has access to the whole file structure. So basically, it can traverse and decrypt all files down below. And the same is true for the beta. So we can see that the beta private key can decrypt the file B, R, Z, and also Q. So we can say that the Q is shared between the private key alpha and beta. So both so owners of those keys or can simultaneously access this Q file. Now, having this structure, let's try to encrypt those files and see how we can store them securely on the IPFS network. But before that, I would like to explain this legend we have for this scheme. So as we discussed previously, we assume that the content is encrypted with DAG CBOR, and the red rectangle means the canonical CBOR basically. This is important pictogram, which means that the content inside the rectangle is encrypted with the key A. Key A is a content key. It's an ephemeral key generated specifically for this box. And this block has address indexed by some number. MC is for multi-codec, and this index is for multi-hash, and we can say that multi-codec plus multi-hash basically gives us a content identifier. Next we have our private keys, alpha and beta, which is used to encrypt and decrypt the content. And here we have our COSE encrypt structure. And as we know, the COSE encrypt basically includes the data about the key material used, the key distribution method, some key agreement metadata, etc. So we have this pictogram would mean that the COSE encrypt describes the key X wrapped for recipient alpha. That means that we have random ephemeral key X generated and wrapped using AES wrapping mechanism for alpha. So alpha, the owner of alpha private key would be able to unwrap the key X and decrypt the actual content. And here we have additional authenticated data, which is also part of the COSE specification. It basically allows to attach any arbitrary key value data for decryption process. So whoever tries to decrypt the content must provide the same data to be able to decrypt the content of the container. Okay, that being said, I think we can move to the most interesting part, which is content encryption process itself. Okay, let's look again on our file structure. So we have S and X files, which are our leaves, and we start with them because we have to start in reverse order. So we encrypt the leaf files first because they don't have links, and when we got their content identifier, we can put them into the upper file basically. So let's see how we do this. So we have our file S, which is just a text files or CBOR. So we generate the random ephemeral key S and encrypt this file with this key. And then we have our second file, which is an image, and we generate ephemeral key X and encrypt the X files. At this point we have, and we upload those files to IPFS, just as we normally do. At this time we have their content identifiers, which is 0 and 1, and we can use them to put their to their parent file, which is P. So we create the file P and referencing our files S and X. So here we have our multi-hashes, and we have multi-codecs. So we have DAC-CBOR and JPEG for X. These are basically our normal content identifiers. So far so good. We have our content encrypted and linked and uploaded to IPFS, but we need to provide the information about the encryption process, and it also has to be available on IPFS. So as we discussed earlier, COSE encrypt structure is meant to contain the information about the encryption process and the key materials and key distribution methods, but it also allows to detach the content. So we can fully separate the information about the encryption process from the ciphertext itself. So we basically create a COSE encrypt structure, and we put the information about the S. So we have this S key here, and we have COSE encrypt structure, which describes key S, and we wrapping it for alpha private key, because these files belong to the owner of the alpha private key. So we also can attach some additional application data, and we need to provide the link to the file S. So at this point we have link to the file S, the COSE structure, which describes the encryption process, and we have additional metadata. So having these pieces of information together basically allows us to locate the S file, figure out the way it was encrypted, and decrypt the content. So we have this structure, which is a simple CBOR object, and this second array contains links to other files which need to be included in the S file, but since S is a leaf, it doesn't have any linked files, so this array is empty. And this meta information is also encrypted by another key, which is P. it is the same key we use to encrypt our parent file P, because when we traverse the graph, we decrypt file P, and we see that we need to link two files, so we need to be able to decrypt them, to locate them, decrypt them, and link and include into file P. So therefore, this meta information about the linked files is encrypted with the same key as the file itself. Now let's take a closer look on our file X, which is a bit different. So as we already discussed, the file X is referenced in document P. Therefore, we have X reference here, and we have the metadata structure for file X. We have COSE document for file X, additional application data, and the link to file X. So this would be our structure. But document S is also, the very same X document is also referenced from another file, file Q, which is part of the different file structure. And if we consult with our initial diagram, we see the file X is referenced from Q and P. And we also know that Q is part of the document tree, which is encrypted with the private key for the private key beta. So it should be available for both alpha and beta private key owners. So let's see how it's reflected in our structure. So we have file X encrypted with the ephemeral key X, and we have metadata for alpha, and we have the same metadata for beta. We have the same link to file X, we have the same application data, or it might be different application data. And the most important thing is the COSE structure, which has ephemeral key X wrapped for beta private key. So basically, the number of these metadata structures is equal to the number of keys which should be able to decrypt the specific files. Now let's apply the same technique for our file Y. So we encrypt the content and upload the file. Then we have content identifier, which we can use to reference these files from our parent files. So we put content identifier Y into this file, and the same content identifier into another file. So now we have referenced it from two different files. So we uploaded everything to IPFS, and now we have to create the metadata structures and also store them on the IPFS network. These will be the set of metadata for file Y. So we can see that the content identifier, or the multi-hash, is has index 2, and we have these structures all referencing the same multi-hash, and the application data. And we have the only difference is that the COSE structures and what key described there. So for example, since this file R is only available for the owner of a private key beta, we have one structure where the content key Y wrapped for the beta private key. And file Q is a bit different because it is part of two data structures. It basically available for alpha and beta, and therefore we create two structures, one with the content key wrapped for alpha and another one with the content key of y wrapped for beta. So basically, when either of our private key owners traverse the graph, they both would be able to decrypt the queue, because they would have access to the queue and content key, and they would be able to use the same content key queue to decrypt these metadata structures, where each owner would use its private key to unwrap the key of y, and basically locate the file y, decrypt it, and include in the file queue. Now, when we have all our all leaf files encrypted and stored and linked, we can go upper and apply the same procedure to our parent files. So we use the same technique, which is generating random keys and encrypting the content, and then we upload these files, getting their content identifiers, and then we referencing them from our parent files. So we have p file here and q file here, and q file also referenced from file b. Right, and now we also have to prepare the metadata information, with the only difference this time that we have linked files inside our files. So let's take a look on our file p. So we have content key p. So we create the structure. So we wrap content key p for alpha private key. We put the reference to this file, which is here, and now this link section comes into play. So it basically shows that in order to be able to link these files, we need to find the metadata for them, right? And this section contains the multi-hashes of the metadata files, which points to the linked files. So when the owner of a private key alpha will traverse and decrypt these files, so he would be able to locate the actual file, locate the information about how to decrypt these files, and also he would be able to get the information on how to decrypt these links, these linked files. And the same is applicable for Q file, with the only difference that the Q file is referenced from two files. So therefore we need to repeat this procedure twice. So we basically, again, we have this content key, which we wrap for beta and alpha keys. We use the same content identifier to point to the file itself, and then we have two sets of metadata on how to decrypt the links. So for example, for our private key beta, we need to link these two files, and if we find them like 13 and 14, so we have 13 and 14 here, and we'll be able to decrypt file X and file Y, which is these two files. So at this point we basically have all the information needed to traverse the graph for either of these private key owners, and they would be able to decrypt, locate and decrypt the content itself, and also by following this link section they would be able to find the metadata about the linked files as well, and they will be able to decrypt them and include into file they actually currently working on. So another interesting property I would like to point at is that as I mentioned, we start encrypting content from our leaf files, and then we continue the procedure until we get to the top of our graph, because we need to get uploaded file content identifiers first to be able to reference them from the parent files, and we also store this create and store this metadata information for each layer, but the uploading of the content files and the metadata are not necessarily synchronized. So this means that we basically should be able to encrypt all the content and upload it first, and then we can upload the metadata files after all the content is already uploaded. So it gives a bit flexibility, so we can either do it in parallel, so I mean we are uploading the content and we prepare the metadata and store it on IPFS, or we can do content first and the metadata later. So it's just a nice feature, I think, for application optimization. Once we have all the information including content and metadata uploaded and stored on the IPFS, let's talk about what kind of information we actually need to retrieve all the encrypted data. And it appears that the amount of information we need to fully decrypt and traverse the graph is not that big. So let's take, for example, our private key alpha, or a user alpha, if you like, and these would be the Merkle root of the file tree encrypted for private key alpha. So we will need to have the content identifier of the Merkle root, which we have here. We need links to the metadata of first level linked files. This would be this information, where we also need to have the COSE structure for the Merkle root itself. So we have content key A wrapped for alpha here. We might have optional application data as well, and we need the private key alpha itself. So having all this information at hand, we'll be able to locate the file, to apply the cryptographic transformation using our private key, and decrypt the content of the file A. Then where we would find two linked files, and we will be using these two links to find the metadata and decrypt them. And then we apply the same procedure to all the child files and their links until we get to the end of the graph. Now let's talk about some important implications and the features of this protocol. So the first feature I'd like to talk about is selective disclosure. And we need to get back to our file structure. So imagine a state where we only have these files encrypted and uploaded. So we have only one private key or user alpha, and there is no beta at this point. And now we want to share some data with the owner of private key beta or a user beta, and we don't want to share everything. For example, we want to keep file P, S, and A for ourselves, but we only want to share, for example, file Q and everything which is below, so X and Y. So as we know the information we need to be able to access any subgraph is this one. So we need this structure and the private key, of course, to be able to access any part of the encrypted graph. So in order to share information with beta, we need to retrieve our file Q and prepare the metadata. So we have our file Q, and now in order to share with the beta, we need to prepare these piece of information. So we need to take content key Q and wrap it for private key beta and provide the links to provide content identifiers to the linked files and the content identifier of the file itself, the one we sharing. So the Q file would be the Merkle root of the subgraph we want to share with beta. So and we can transfer this information to beta in some like secure media, which is out of the scope of this protocol itself, and then the beta would be able to access the data and maybe, for example, include file Q to some other file which the beta user owns already. And that would be basically a selective disclosure feature. So we can take any part of the encrypted data and share with another user by providing the metadata, which is encrypted for the private key of the user we want to share with. And this protocol also has some improvements over the privacy aspect, because, for example, when we're preparing the pin set for the pinning service, we collect only multi-hashes from our metadata, and we don't even need to leak the information about the file, the real file types or multi-codecs. For example, we can use some raw binary codec and construct the content identifiers on the fly. So we take the multi-hash from the metadata, append the binary multi-codec and create the CID this way, and deliver it to the pinning services, because the the information about the real content types or codecs, it is only accessible inside the file content. So only when you traverse the content and decrypt the actual content container, you can get the information about the type of the files you want to include. The metadata structures do not contain these multi-codec parts, so they only operate on the multi-hash level. So when the application traversing the graph, it can actually build the CID on the fly using some obscure multi-codec, like binary, for example, and therefore not avoid leaking this information to a pinning service, for example. So this is also a nice feature from the privacy point of view, which is important for the project we are working on. Okay, I think this is everything I wanted to present to you today. So it was Vsevolods from Blockvis and Identity.com presenting the new protocol for storing encrypted data on IPFS. Thank you.